Hello, Professor
Good
Mark.
morning.
Arul here.
Good morning, sir. Good morning, sir. Yeah.
Hi.
How you are, sir? Fine?
Good. And how are you?
Good,
So
good.
your program must be going on, right?
Yeah. It's going on. Now,
Okay.
first session has been completed. First
First
session.
session has been completed. Okay. You have
Yeah,
a
yeah.
break now.
Yeah.
Who was the first session?
Professor V. Ravi Shankar from IIT Delhi.
Yes. You have a very nice set of speakers. Congratulations on.
Yeah. Thank you, sir.
Yeah.
Actually, we have started this program in our institute
I see.
since since 2012 in MTech and BTech courses.
Or you have both MTech and BTech in this
Yeah.
quantum information or
Quantum
computing.
information.
I see.
Because this is Information Institute, Indian Institute of Information Technology.
Uh,
So I should take my privilege to have a physicist and
uh,
take this opportunity to introduce this course.
very
I am
nice.
in this course in this institute,
Oh,
and
okay.
students are very much taking interest in this subject.
Yeah. Yeah, it's a trending subject, so it's very nice to see this overall interest.
Yeah,
Um, yeah,
really.
sometime back, I think there was IIT Dharwad. Dharwad had some
Ah,
program on this.
okay.
So nice to see so many IITs. Hyderabad has a very nice program
Very
already.
nice. Yeah.
So yeah,
Mhm.
I see.
Actually, this is Gwalior is was the first triple IT in the series.
Is it? Oh,
Yeah, it is the first triple IT in the series that is established in 1998.
oh, the Gwalior one is 1998, is it?
Yeah.
Oh, I see. I didn't know that. So Gwalior is a historic city. I've never been there. I saw on Wikipedia a lot of nice things.
Really, sir, if it would be having offline mode, then I would sure invite you to visit
Yeah,
here.
that'll be great. Yeah, I mean it's. I've been to Bhopal,
Yeah,
outdoor, but Gwalior, no. This is
yeah.
something which we have only read of in history books. And
Okay. So you
so
must
your
visit.
audience is all your faculty or other people are also there.
No, other people from all over India.
Oh, all over India. Okay.
Yeah, they are faculties, young faculties, and research scholars.
So my talk is quite elementary. Is that okay, or how should
Yeah, that's true.
it's okay?
Because this is emerging area, that's why they need some require basic elementary knowledge about this thing. And people are joining just right now.
Shall I share my talk and see how it is going?
Yeah. Sure.
Yeah, I'll
Yeah,
share it.
yeah. Yeah.
You can see this, Pankaj.
Fine. It's fine.
Okay, good.
It's fine.
Yeah. Okay, very nice. Should I stop sharing or should I just let it just be there?
No problem. So it's remain it here. No
It
problem.
can be there, no? Okay, good.
Yeah.
Okay.
How is the weather, sir? There?
It's raining, so it's nice and
Oh,
yeah,
that's
Chennai,
okay.
So it's a bit of a monsoon will come now, right? So
Yeah.
yeah,
I visited Chennai once when Icon site was organized in Chennai.
you
Icon
came to
set,
check.
Icon set
Uh-huh.
conference on nanotechnology.
Yeah. You were there in IIT Madras?
Yeah.
Oh, very nice. Yeah. We
Professor
have a
Bala,
good nanotechnology program. Yeah.
yeah, Professor Bala is there. I think.
There is Ramaprabhu,
Yeah.
Pradeep.
I think he has been retired now.
Let me just close the door and come.
Sir, I think online classes going on in IT Madras.
Hello?
So just I'm asking that IT Madras is holding online classes only, right?
Yeah, absolutely.
Yeah.
Even next semester, it's going to be on.
Okay, fine.
I'm sure it's the same case there, right?
Yeah. It's same case.
Slowly, students are coming back. So, I mean, some batches are here.
Yeah.
If things don't become worse, some more will come next semester. But nobody is confident enough to have classes yet.
Yeah.
We are just having meetings and some seminars,
Hmm.
just
Okay.
just starting.
Hmm. Actually, there is a problem in hostels.
Exactly. That is
That is the
also our problem because we are a
yeah.
residential institute. We cannot open up.
Uh,
We have to have only so many people in the hostels.
yeah.
So, so how many? What will be the student strength there?
Here is that is about 5 year integrated course in information technology. There is one course, information technology, 5 year degree course, where a student has choice of taking after 3 years MBA or MTech. That
Okay,
is 5 years. One another course is of BTech Computer Science, 4 year. There is another course of MTech Computer Science, 2 years,
I see.
and MBA 2 years.
I see.
So nearly about you can say in 1200 or 1400
I
students,
see.
including PhD students are also.
Ah,
And this is also residential campus,
okay.
fully residential.
Mm. I think all the triple ITs are like that, is it?
Yeah.
Yeah, I think
All
triple ITs are residential.
like central government funded, which are they are all residential campuses.
Public-private enterprise, right? You will have also some in.
No, we have from the central government.
I see. So you must be one of those
Yeah.
unique
There are
ones.
four central funded institutes, IIT,
Okay.
like Gwalior, IIT Allahabad, IIT that is here Jabalpur,
I see.
and one is in your Chennai, sorry, in Tamil Nadu also.
There's one in Trichy. I think there's one in Kanchipuram and
Kanchipuram, yeah, IIT Kanchipuram. That is also centrally funded institute.
yeah.
And thereafter, we have all other triple P mode IITs in all states.
Okay. That's a structure.
So I think, sir, we should start.
Yeah.
People are,
Yeah.
yeah. So good morning to Professor Lakshminaryan, and welcome to this FDP program on quantum computing. So let's start at brief introduction about Professor Arul. Professor Arul Lakshminaryan is a professor and head of the physics department at IIT Madras, and he's a theoretical physicist with a PhD from Stony Brook, New York. He was postdoc and later faculty at Physical Research Laboratory, Ahmedabad. He joined the faculty of IIT Madras in 2003. Long-term visiting appointments were at Washington State University, Pullman, IIT Kanpur, and Max Planck Institute for Physics of Complex Systems, Dresden. Part of his research interest includes quantum chaos, quantum information, quantum walks, many-body systems, quantum classical correspondence, mathematical physics, and random matrices. His research highlights includes quantum information and computation, pointed out that quantum chaos engenders large entanglement among bipartitions of pure states while destroying entanglement among small enough subsystems. Quantum many-body systems and information, like pioneered studies on many-body quantum entanglement, integral and non-integral systems. Many-body localization was studied from the point of view of local entanglement, quantified the effect of local unitary operations on global entangling power, and found many entities concerning cyclic sums of Jacobi elliptic functions, phenomena that product of random real matrices limit to have entire spectra in the real domain. To his credit, he has about more than 75 research papers in referred journals, and they are available everywhere nowadays. So this is just a brief introduction of Professor Arul. Though he is a very active worker in quantum entanglement, quantum computing, and doing a lot of research there and his group. So I welcome to Professor Arul and invite him to start lecture. Yes, Professor Arul, sir.
Thank you. Thank you very much, Professor Pankaj Srivastava. It's a pleasure to virtually be in Gwalior, and thank you very much for the very kind introduction and invitation to this program. It's always a pleasure to talk about what you love doing, and quantum entanglement is certainly one of those things. And let me request that since this is a online talk, and in this particular mode, I can only see my screen. I would like any intervention. Please feel free to intervene and interrupt, ask questions in between also. I have no issues, but you will have to talk, or probably Professor Pankaj has to mediate.
Yeah,
How
sure.
does it go? Yeah.
Yeah, sure.
Yeah. So
If anyone wants to open their videos and interact, that would be more beneficial if you open your videos. I request the participants.
But I
that
can't
would
see them, Pankaj. So the thing is,
yeah, that would be more lively if you, because this is something online going on.
yeah. Yeah.
And if you are open your video, show your faces, then it look very lively. Okay.
Yeah, but I think when I'm sharing this, I can't see the screens.
Okay, no problem,
So,
sir. Yeah,
so
yeah. I will show
yeah, yeah.
to help
So,
you.
right. Okay. So, at least that is what I think. I don't know whether I can both see the audience and see my screen. Probably not possible. So let me not try that. Let me start off
Yeah.
and say hello to everyone who's there, and welcome to this. This is going to be an quite an elementary, basic introduction to properties of quantum entanglement. If you're an expert, please bear with me, and I will tell you some. I'll give you an introduction, overall introduction to entanglement, and then introduce the necessary mathematical tools, and then go to the main subject of entanglement and bipartite entanglement. That is entanglement between two objects or two parties or two subsystems, which is the most basic thing that one can do, but very important one. And then into some aspects of multipartite entanglement, which includes things like mixed states. And then I'll just mention a few applications. Okay, so that's the idea. And we have a new center. We have actually a couple of centers based on our Center of um, Institute of Eminence funding. So we have started a virtual center for quantum information theory of matter and space-time, which includes string theorists, quantum information theorists, and mathematicians. Um, so we're just starting our activities. It's just a small advertisement for that. So actually, it's quite remarkable that those who developed quantum mechanics at the beginning of last century already understood the strangeness of quantum mechanics very early, and they have pinpointed the important aspects about quantum mechanics, and one of that was entanglement, which was realized by Schrodinger maybe about 10 years after he himself developed quantum mechanics, as we study it in our textbooks. Here I have a quote translated from German, 1935. When two systems enter into temporary physical interaction, and after a time of mutual influence, the systems separate again, then they can no longer be described in the same way as before. I would not call that one, but rather the characteristic trait of quantum mechanics. The one that enforces its entire departure from classical lines of thought. By the interaction, the two representatives, what we will call quantum states, have become entangled. So, this is how Schrodinger first wrote about entanglement. He said it's not one of the characteristic traits of quantum mechanics, but the characteristic trait of quantum mechanics that forces its entire departure from classical lines of thought. So, as we go by, we would understand this statement better, but let me emphasize a couple of things. When two systems enter into temporary physical interaction, that means that he's saying that there are two systems, they come into contact temporarily. So you turn on an interaction, turn off an interaction. And what he's saying is that before and after, we cannot describe it in the same way. What exactly this means? For example, let's take a classical situation. We have two particles, let's say that they are not interacting, they have their positions, they have their momentum. And let's say that that is the state of the classical system. And let's say that we turn the interaction on, and after the interaction is over, let's say that we switch it off, the state is still described by the same set of variables, namely positions and momenta of the individual particles. Of course, they will change because of the interaction. But there is no difference in the way the state is described before and after. They are just points in some phase space. Whereas what quantum mechanics does, it's saying is that if they are interacting, then the qualitative nature of the state is different. So this is what Schrodinger is saying here. And to make it even more, to say what is even more peculiar about this quantum state after the interaction, is that this statement here, which I have highlighted, the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts. So just read it again. The best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts, even though they may be entirely separate. So to understand what this means, again, take a look at, let's say, this classical state of two particles. Let's say that they have interacted. You have position and momentum of each of these particles, which describes its state. That is the whole state. Now, if you give the position and momentum of both the particles, suppose there were two particles, then of course you also know what is the position and momentum of the individual particles, isn't it? So, however, if it's a quantum state, you may know the entire quantum state of the two particles together, but if suppose somebody asks you, okay, now what is the state of particle number one, we cannot answer this question. And that is the nature of this entanglement, that there is a knowledge of the entire system, but does not imply that we know the best possible knowledge of all its parts. So it is rather discomforting that the theory should allow for a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of his having no access to it. I will come to this second part of it, it's slightly more involved. So let us look at this as mathematically. I found on Wikipedia that in the page about Gwalior, this is Miharikula coins. So coins from ancient Gwalior. There is clearly a head, and let's say that this is tail. Okay, let's say that there are two coins. One of it, now just imagine classical coins. So there are two coins and the state is simply head or tail. We don't bother about position, momentum, and so on. So let's say that the state is just the state of whether it's a head or tail. Then how many possible states are there for these two coins? Well, clearly there are only four. Both of them can be heads. One can be head, tail, head. Both can be tail. So these are the classical states of these two coins. And if you specify the state of both of these coins, let's say that head, tail, obviously you know what is the state of coin number one. It's a head, and the other one is a tail. We know that. And this is, of course, just a ket that represents a quantum state. I'm assuming that you have the background to understand this, but if you don't, this is just telling you a description of state of the first particle is tail, state of the second particle is tail. What quantum mechanics does is it says not only are these states allowed, but even superpositions of these states are physical states. So, oh, sorry. I should have gone into a slideshow. Yeah. So now you look at this state. So this is a possible quantum state because the superposition of such states are also quantum states. This is the very important thing about quantum mechanics, that superpositions are also states. So you can just superpose these. But now if you ask, what is the state of coin number one? Is it head or is it tail? This is unanswerable. Although we know that the state of both of them together is this perfect state, we cannot say what is the state of coin number one or coin number two. If you make measurements on the state, then if the first coin can be either head or tail with equal probability. So this is an example of what would be called an entangled state. Namely, entangled states are those states of joint systems of, let's say, two particles, such that their two particle state is a pure state, can be specified exactly like this, but the individual states cannot be pure states. What exactly they are, we will see in a minute. I will also define formally what is entanglement. So, okay, that is fine. I mean, this is something that looks very abstract, but in fact, a lot of chemistry and atomic physics, and therefore our own existence depends on the existence of entangled states. They're not uncommon at all. But what would be uncommon is if you had two such coins and they can be well separated in space so that experiments can be done. So that is where modern, what Schrodinger's time or even till the 80s or 90s people could not do, we can now do routinely. So one of the simple situations where this can be imagined is polarization of light. So we all know what polarization of light is. It says that here is light, this is some electromagnetic wave. But if suppose the electric field lines are arbitrarily oriented, they can be in any particular direction, of course, perpendicular to the direction of the propagation, then it's an unpolarized line. But if you place a polarizer, it picks up one particular polarization, let's say that along the vertical direction. Okay, so this is a polarizer, so these are all very available things. And then if you measure the polarization of this after it has already been polarized, you will get perfect vertical polarization. But suppose you were to tilt this polarization 45 degrees, let's say, then you would have a 50-50 probability of getting either vertical or horizontal polarization. So suppose it is suppose it's a cross polarization between both of these things. It only allows, let's say, vertical and horizontal polarization. Then you will get 50% light here and 50% light. So polarization degree of freedom is like this head and tail. So we can think of polarization, vertical polarization. There are only two aspects of polarization, two independent direction of polarization. Light, which also, by the way, is a quantum property of a photon through its spin. So we can look at the spin of the individual photons as a qubit state. A qubit is nothing but a two-state system, as I will say here. But let's just look at this now as a horizontal polarization is state 0, vertical polarization is state 1. Then these 45-degree polarization is just superpositions of these. So that it can be 0 plus 1, 0 minus 1, for example. It's 135-degree polarization. Now, so these things are not independent. These polarizations are not independent. It's just linear superpositions of these. And we can get that by just doing appropriate changes. Now, that's all a single photon. So a single photon can be polarized along this or any linear combination of this, any linear combination. These are just two of them. But what is interesting is that there exist crystals such that you can do what is called down conversion. So there is a frequency, a particular frequency of light. It splits into two different frequencies of photons. So that's a down conversion. The frequencies are down converted or reduced so that energy is conserved. But now you have two photons coming out which are polarized, and actually they will be polarization will be also correlated. So what is interesting is you'll have a cone coming out which are horizontal polarization, cone coming out that is vertically polarized as is written here. But what is interesting is that some of the photons will be in an intersection of these two cones. And when they are coming out from this, you will have two photons coming out in very different directions, but they will have a joint state, which you can't say whether it is in the horizontal polarized, whether the first one photon is horizontally polarized or vertically polarized. So in fact, the state that describes these photons which are coming out in this intersection is exactly like the a state which I wrote of this coin, head plus tail. It's exactly like that. Here it's horizontal vertical plus vertical horizontal. So if we take a photon which is coming out from here, we cannot say whether it is horizontally polarized or vertically polarized. Even if you pass it through a horizontal polarizer, it will give you 50% it will be horizontal and 50% it will be vertical. But even worse, as I will say in a minute. So the peculiarity of these kind of states is what is peculiarity of entanglement. So let's look at it a little bit more carefully. So we have these two photon polarization entanglement is given by the state, which is horizontal vertical plus vertical horizontal. So there are two photons A and B. Okay. Now, suppose we make a measurement of the photon A using an X filter, then we know that the photon B will certainly pass through a Y filter, because we would have got 50% chance that it was horizontally polarized. Then we would be saying that this is the state of A, but then we know what is the state of B. If suppose this is horizontal, that is vertical. And therefore we know for sure that photon B will pass through a vertical polarizer with probability 1. Okay, so we would call such a situation classical correlation. These two photons are correlated, but still I would call it classical because actually this will be true even without the superposition. You see, even without the superposition, without the second term, let's say, if this is horizontal, then that will be vertical. Okay, suppose you choose this. Uh, so let us just go on. Okay, but what makes this state very interesting and quantum mechanical is that we may now choose to measure this photon A's polarization using a 45-degree filter. If we did using a 45-degree filter, suppose, for example, we don't have the second part of this. We had only this part of it. Then you will get 50% chance that it will be going through a 45-degree filter because it's horizontally polarized. What about photon B? The same 45 degrees filter will be used by B, let's say, on photon B. Then there will be still 45%, I mean 50% chance that it will go through or it will not go through. That is, it will look random. There will be no correlation between these. What was initially what was initially perfectly correlated, if you had a filter which was X or Y filter, will now look completely uncorrelated if you had 45-degree filters. However, if it is this polarization entangled state, this is where the magic happens. This can also be written as this. This can also be written as this, where this is now these two are 45-degree, 135, 45, 135, or 135, 45. Okay, so there is, so now if you measure using a 45-degree filter, and if it passes through 50%, it will pass through A, then you know for sure that the other one will be a 135. It will pass through a 135 filter. And therefore, there is complete correlation, even though you have changed the measurement. You have now chosen to change the measurement, there is still perfect correlation. It's as if photon B knew what was going to be measured of photon A, although they can be space-like separated. That means that there is no light, no speed of light signal that is passing between A and B, but still there is a correlation. So this is what actually Schrodinger was worried about when he said it is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of his having no access to it. So for the photon B seems to be, polarization of photon B seems to be at mercy of what is going to be done to photon A. And this is quantum correlations, and this is a result of the entanglement which is present in this. So in a sense, it's a super classical correlation. So that's why that's what Schrodinger said when he meant that. That's what he meant when he said that the whole is a definite state, whereas the parts are not. And as you know, there is a famous paper by Einstein, Podolsky, and Rosen where they argued that if you assume that things are local, that is, you cannot affect distant uh, objects fast, or if you have realism, that means that properties are already there of a system before you measure them. Measurement is only revealing pre-existing properties. It does not violate any principle of relativity, which says that no signal can go faster than the speed of light. So let me stop here and ask if there is any clarification.
Yes, any questions from participants?
Okay, let me go on, maybe later on. So
Yeah.
now let me introduce the heroes of the game, namely qubits. You might already have been introduced, but let me just introduce it in this context. They are simply two-level systems. Okay, so as you know, quantum mechanical systems have many energy levels. An atom will typically have infinite number of energy levels. But if only two of them are relevant, you would call them a two-level system. And qubits are nothing but two-level systems. So a classical bit is a two-level system of on and off, or 0 and 1. And a quantum system is something where the Hilbert space is only two-dimensional. So it's the simplest quantum system possible in that way. Or it can also say it's the most quantum system possible because there are only two orthogonal states. It's like the photon states which I was talking about. So if the states are typically they're denoted as 0 and 1, they are orthogonal. That means that if a state is a 0, probability that if you measure it, you will get 0 is 1. Okay, so they're orthogonal. Probability that you get 1 is 0. And any superposition of these two states where alpha and beta are complex numbers is also a quantum state. As we know, we have atomic levels, like in this case, atomic levels. Suppose this is an S and a D level, an electron can be here or here. This can be a two-level system. Here there is a third level, but you can ignore it. That is actually used for some measurement purposes. You can shine a laser of this frequency, and then you can put the electron into this state. But this would be a typical transition, let's say. So this would be a two-level system. But if you have two such atoms, then they can be in such entangled states as what I wrote earlier. In fact, this is an example of a Bell state. If you have three, they can be in even more entangled states, such as this. You have three atoms, three of them are in ground state, or they can be also in excited state, and it's a superposition of these two. Now, what sort of a state is this? So this is a multipartite entangled state. In fact, it's got a name because these people studied this state and pointed out its peculiar properties. So such very simple states are very important states in quantum information. It's called a GHZ state. So there are many, many milestones in quantum information. You have a very excellent program. You already listened to talks by experts, and I'm sure that many of them are talking about these things. Let me also say that this is sort of very roughly milestones that what happened. In the 1960s, John Bell took the EPR assumptions of locality and realism and made it into a testable inequality, testable in experiments inequality. So he said that there is some correlations which you measure of these two particles which are entangled. You, let's say there's some correlation between two observables and some particular combination of these measurements on both sides. Then if there is locality and realism, there is a certain inequality. Say some quantity is less than 2, and whereas if it is violated, it is greater than 2. That is in fact called a CHSH inequality, after developed a simpler inequality than what Bell had. Then there was a no cloning theorem in the 1980s, which pointed out that unlike a classical system, like we have a Xerox machine, it doesn't care what you're going to copy. It doesn't say that I will only copy Hindi text and not English text. So whatever may be the state of the paper, it copies faithfully. So any unknown state, classical state, can be copied. Whereas quantum mechanically, this no cloning theorem assures us this is not possible. We cannot make copies of an unknown quantum state. And then came a very remarkable development called quantum teleportation, which I will talk about a little bit later. And then you know that there are various applications with quantum cryptography, which is a very well developed field of technology now, where we use the fact that quantum mechanics is sensitive to measurements to ensure some security, which is not there in the classical case. And then quantum computing became a very big subject when there were some algorithms which were developed, which were very powerful compared to classical algorithms. So one is the short factorization you might have heard about, or you will hear about, where it factors numbers into prime factors very efficiently. We don't have a classical algorithm which will do that. That's why actually a lot of our credit card transactions and so on are protected by this. And then there is a search algorithm, a Grover search algorithm, which is searching in an unsorted database. Again, this is something which, so these two are very famous algorithms. There are many other algorithms, and algorithms are being developed these days. It's in fact one of the major tasks of quantum computing is to come up with algorithms, quantum algorithms that have a classical advantage over classical. And you know that there are now qubits like these that are realized in experimental systems and which are actually available to us. Like you can access a 5-qubit IBM machine, so to speak. You can program it. You can run some of these teleportation and other schemes on that and learn. If you pay money, you can get a bigger number of qubits. I think now there are 60-qubit machines that are available. Very soon they'll be scaling up to hundreds of qubits. And then it becomes a real quantum computer. So all of these developments are leading up to the development of quantum technologies, of which quantum computer is one of the important technologies. So let me skip over this. There's a Bell inequality test that I talked about, which uses entangled electron spins separated by 1.3 kilometers. So it's a very remarkable paper. So usually, 2015, usually Bell inequalities were tested with photons, which can be easily entangled and separated by large distances. Here, electron spins that were entangled but separated by large was used to test this Bell inequality. And as I told you, there's a particular quantity which, if it's larger than 2, is a violation. Here, I think it's going below this, but it is more than 2. This last line is not coming in this thing. So they performed these experiments, and they conclusively showed that Bell inequality was being violated. Okay.
Hello, sir.
So So what are the uses of entanglement apart from its fundamental nature, which itself is very interesting and worthwhile for us to study?
Sir,
uh, yeah,
Mr. Ankur Biswas is asking some question.
yeah.
Yes, please, Ankur Biswas. Yeah. Clear, Ankur Biswas. Please unmute yourself.
Hello, sir.
Yeah.
So I am not basically from computer physics background, so might be my question is a little bit novice. So the thing is that whenever we are seeing the alpha and beta, why we are always considering it as a complex number? So that's my question.
Yeah, good question. Uh, this goes back to why the Schrodinger equation, the states can be complex. So the states, not only can they be complex, it is essential for us to consider them as complex. Of course, you can have alpha and beta to be real too. I mean, they can have 1 by root 2, 1 by root 2. Okay, there is not a problem. That is also a state. But the general state will have complex, should have complex numbers there. Because the general Schrodinger equation, if you look at Schrodinger equation, which I have not written down, is the equivalent of Newton's equations. It says that if you have a state, the time evolution of that state is given by e to the power of I times the Hamiltonian into time. So that I is a very essential thing, and that is what is giving rise to I is square root of -1, is giving rise to these states. Now you may ask, is it possible for us to do quantum mechanics without imaginary parts in it? Because after all, when we make measurements, everything is real. Probabilities are real and so on and so forth. Schrodinger tried this for 1 year. After he found what we call Schrodinger equation, he was asking the same question as you and was actually worried that it was incorrect. And he tried for 1 year, came up with something which he thought was a solution, and then gave it up when he realized that it did not actually, there was a problem. So I cannot go into the detail of, I mean, it's not, let's say, obvious or something like that as to why the state has to be complex, but this goes back to the basics of quantum mechanics, that the that for a complete description of all the states of a physical system, indeed you need to have complex numbers. For example, if you take just this 0 and 1, uh, if you restrict yourself to only a real alpha and beta, you will get a subset of states, which, like for example, the 0 and 1 can be what is called a um, like the spin systems which we have here. I've called this to be, let's say, spin up and spin down. Okay, let's look at it as some magnetic spins up and down. Then there are some operators which you can do and shift these states around. For example, if you have a magnetic field along the x direction, that will change the state of this system. That will change the state of the system, and it can make it 0 plus 1. Okay, so you can imagine the state as being pointed to the right here. But suppose you apply a magnetic field along the y direction, then where does it go? You see, if you apply a magnetic field along the x direction, you can rotate this vector all over this place. And you will get all possible linear combinations of 0 and 1. However, it is possible to apply a magnetic field along the y direction and rotate it, and then you cannot describe those states as real combinations of these. You will need complex numbers to come. So what it means is actually, when even if you look at it from a physical point of view, not all possible states cannot be realized by just real operations on the states. Okay, I don't want to go into more details on that, but it's a
Thank
good
you very
question.
much.
You can read that.
Thank you very much, sir.
Any other? So let's carry on with teleportation. What does it mean? So these are the people: Bennett, Brazard, Propos, Joja, Perez, and Wouters, teleporting an unknown quantum state via dual classical and Einstein-Podolsky-Rosen channels. So that looks like a very complicated title, but It's a very interesting one. So it's a very those of you who watch Star Trek, there is a famous line there, "Beam me up, Scotty." So I believe Captain Kirk is going to be blasted out into space, really, for real, at the age of 90. But in this serial, he would say, "Beam me up, Scotty," when he wants to go from, let's say, Chennai to Gwalior instantly. So he would be dematerialized in Chennai and would be materialized again in Gwalior. Maybe it's the speed of light, but because we don't want to violate that, but that's still much faster than taking a flight. So that sort of a scenario is a very science fiction scenario, but that seems to be possible if you have an entangled pair. So let's say that A and B share an entangled pair, and I'm just denoting this like this. So there are two squares, and this entanglement is described by these arrows. Okay, so these two are this entangled pair, like the 0, 0 plus 1, 1, or this photon. These you can imagine them as polarized photons, which are here and here. And A has another qubit with her, whose state she doesn't even know. Let's call that S. And she has this state, she doesn't know what it is. Bob here has one pair of this entangled pair. So actually in this cartoon you can see this here. So uh, Alice has a yellow photon. Charlie has a pair of blue photons that are entangled. Okay, so these are now entangled, and Charlie sends one of these entangled pairs to Alice, and one of the pairs to Bob. Okay, so we have this kind of situation. So Alice has two photons with her, one whose state she doesn't really know, we are just calling it a yellow photon, and one which is a pair with Bob, which is entangled. But she doesn't care about that. Now, what happens? What is the aim? The aim is that Bob's particle should acquire the state S. You see, Bob's particle, after the end of the protocol, should acquire the state S. So this should be the situation. Bob should have the state S. So this is the teleportation. This unknown particle's state, it doesn't matter what the state is, it will appear magically at Bob's end. Okay, so this is the end of teleportation. Now let us just think about it. A question was asked just now, why should alpha and beta be complex? But in fact, even if they are real, it doesn't matter. There will be some irrational numbers maybe typically, or even suppose they are rational, it doesn't matter to me. Suppose you want to convey to someone this state alpha 0 plus beta 1. Then you have to specify two real numbers to that person. How much information is contained in two real numbers? If I want to convey this information of even one real number, you need actually infinite number of bits, because any real number will have an infinite number of bits in its, let's say, binary representation. They may all be 0, but that is information you have to convey to them. So actually it requires an infinite amount of classical information to do this. And this is the cool thing about entanglement. What if you had a maximally entangled pair like this Bell state, it's possible to do this with just two classical bits of information transferred between A and B. Just two, not infinity. And that is achieved uh, in the teleportation protocol. So this is a long way away, Alice and Bob. So finally, Bob's photon or particle or spin must be this yellow photon. Okay. So what Alice does is she takes the unknown photon with her, the P, and the known one that is entangled with Bob's, and she does an interaction between them. And she does what is called a joint measurement. And the result of the measurement can be only two possible bits. And she conveys those two bits to Bob. And then Bob makes use of those two bits and realizes that the photon state has changed. In fact, in one of those two realizations, one of the four realizations, Bob doesn't have to do anything at all. The fact that Alice has done this joint measurements is sufficient for Bob's state to become LO. So it's actually, the more you think about it, the less you will understand. So you have to start thinking about this, and we will see exactly the mathematics of this. But is there at this point any question about just what is the scenario? That is, Alice and Bob share an entangled bell pair. There is an unknown state particle whose state is there with A. A does something to that unknown particle and her pair of the bell state or entangled state, and conveys to Bob one of these four possibilities. And Bob then does something on his qubit pair and finds that that state is S. He can make that state S. In one of these four possibilities, he doesn't do anything. So it's like Alice does something here, and then magically the state S is teleported into the state. So this seems like a science fiction thing, but it's completely possible. And these days, teleportation is done over longer and longer distances. There is ground to satellite teleportation. Now, this is from a Chinese group, Jaiwan Pan. This is from 2017. Overview for the setup of ground to satellite quantum teleportation of a single photon over distances of up to 1,400 kilometers. So this is actually free space teleportation. There is no special, otherwise one may use fiber optic cables and so on to guide photons. This is, of course, this is just between a satellite and a ground station. So we have in India several setups. We are starting off slowly, but I think there are over several hundred meters teleportation has been demonstrated, or at least communication has been demonstrated. I'm not entirely sure whether teleportation has been demonstrated. So now I will go into, I think it's now about half of my talk. I will go into some mathematical tools and then into the nature of entanglement itself. So those of you who are not familiar with the mathematics of quantum mechanics need not actually be very scared of these symbols. They may just be slightly different symbols, but they are really nothing but vectors and manipulations of vectors and linear algebra. So let me be very honest and frank. The mathematics of quantum mechanics is at some level quite simple. So what is the mathematical tool that is describing the state of two particles? The state of one particle is a vector in some vector space. Hilbert space is a very big word for it. You can just think about it as a vector in a vector space. For example, a two-dimensional thing like this photon states that I've been talking about, like the 0, is just a vector with two entries. Let's say 0, 1. And this will be 1, 0. That's all. So now these entries can be complex. That's what we described before. So they are complex vector spaces. That's all. That's the difference between that and a normal vector space that we can imagine on the plane vectors. What about now any linear combination of, so this is actually a vector. So this is a vector in, this is state of particle A. This is the state of particle B. So these I and alpha are what are called basis states, and that can be any thing like the 0 and 1. We'll just imagine 0 and 1. Okay. So it's a linear combination. I'm also allowing for any dimension D, not just 2. If it's qubits, dA will be only 2. It will be a linear superposition of just 2 of them. But you can take in general any A and B. Okay. So now, this symbol here is called the tensor product, and that is what is describing the joint state of A and B together if the state of A is psi A and if the state of B is psi B. So now this joint state is given by these tensor products of these basis states in a very natural way. You see, this AI and B alpha is just summed up over this. AI B alpha I tensor alpha. So this is a state of A and B where A is in psi A, B is in psi B. And this just comes from this tensor product property of distribution, okay, linearity basically. And also this property here that if there is a number which is multiplying psi A tensor psi B, this is also the same as if the state psi B was multiplied by A. Okay, so overall you can take out this A from this and this. So it's a very natural things of a tensor product of states. Exactly how do I represent them? You see, actually it's very simple and interesting. Let's say that we have a state of a particle in 2 dimensions. So it will be A1, A2 vector, where this A1, A2 can be complex. And those of you who know normalization will be in quantum mechanics, the probability will be 1 totally. Modulus A1 square plus modulus A2 square will be equal to 1. Now let's say that the other particle has 3 dimensions. Okay, it's for illustrative purposes. So dB is 3, the dimension of B is 3, B1, B2, B3. Then the joint state is just given by this one, which I just now described here. But written out in terms of vectors, it's very simple. Now you see, the usual vector product, it doesn't make sense. We can't multiply these. But a tensor product, what you do is you take A1, multiply it by this entire vector. You'll get A1, B2, A1, B2, sorry, A1, B1, A1, B2, A1, B3, and then take A2 and multiply it all together. So you'll get a 6-dimensional vector. And that is the dimensionality of the Hilbert space of both these particles taken together. So this is the tensor product notation. And you can similarly define tensor product of operators also, or matrices. So let me just describe to you here, 2 by 2 matrix, 3 by 3 matrix, tensor product. You just take a first element of the first one, multiply it by the entire matrix. Second element of the first one, multiplied by the entire set matrix, the second matrix, and so on. So you get actually a 6 by 6 matrix now by doing a tensor matrix of a product of a 2 by 2 and a 3 by 3 matrix. Okay, so this is actually the mathematics of multi-particle systems. For example, Ising model, which is very popular model in physics, and it's a model of magnetism, for example. It describes the interaction between 2 spins or magnetic, basic magnetic units. You may think about, for those who are not physicists, as sigma z, sigma z. And this J is, you have a collection of spins between J and J plus 1. And this is an external magnetic field, and this is along the X. So again, I apologize for those who have no background in physics, but for those who do, these are just the Pauli matrices. And this is an external magnetic field along the X direction. This is the interaction between the spins. So it's a very important model in this. So, but exactly what do we mean by this? You have many particles, you have many spins. This is not multiplication of Pauli matrices, it's actually the tensor product. So indeed, for example, N equals 2, this is just 2 spins. So this is now the Ising model of the 2 spins, sigma 1z tensor sigma 2z. And then this is now tensor product with identity, and then identity tensor the sigma x direction here. Okay, so this is actually what is meant by this Hamiltonian. And then if you put these sigma 1z, you know, is 1 minus 1, and sigma 2z is 1 minus 1. Now if you apply what I just told you and do the multiplication and then addition, you'll have a 4 by 4 matrix, which is the Hamiltonian of this Ising model. And then you can solve it and get the energy levels and so on and so forth. Or you can get the eigenstates of this Hamiltonian. So this is the basic mathematics of many particle systems. So what is actually the tensor product space? You see, I just described the tensor product like this, but are all states like this? Are all states of a qubit and what is now called, this will be called a qubit because it has 3 states. Are all states of a qubit of this nature? No. In fact, that is the whole point about entanglement. The fact that that Schrodinger realized that it's not only these states here, HH and HT that matter, but also HH plus TT are also physical states. So that's exactly what we need to do. So it's not only tensor product, but sums of tensor products are also valid states. So that is called a tensor product space. It is the space that is spanned by the tensor products of some bases. So you can fix some bases. Let's say basis I in A, basis alpha in B. This will be a dA dimensional space, dB dimensional space. The span of all of this, that means you can consider linear superpositions of these with complex coefficients. That is the tensor product space of entangled states, and that is a space whose it's a complex Hilbert space or vector space of dimension dA into dB. So a 2-qubit space is just a span of all of these things, and that is just a span of these 4 vectors. So in general, a state of a composite system of A and B is a linear superposition of these tensor products of some bases, and that need not be unentangled. So the Ci alpha are any complex coefficients such that their modulus squared sum is equal to identity from normalization. That's all. You don't require that it be of that form which I wrote down earlier. In fact, that will be called an unentangled state. In general, this is not of the form of a tensor product of 2 vectors. In general, this is not true. And therefore, most of this will be called an unentangled state because you can specify what is the state of A and what is the state of B. If you cannot do so, then it is entangled. So in general, you see there will be dA into dB complex numbers, Ci alpha, which is specifying the state. Whereas if it was like this, you'll have only dA plus dB coefficients. And therefore, this is much less. So the number of, in some sense, the measure of volume of unentangled states is 0 compared to the measure of volume of entangled states. How does one find out whether some state is entangled or not? So, but maybe before that, let me use this to demonstrate teleportation, which I introduced. Okay, so now this entangled state, again, so this is the standard basis, this Hermitian operator or Pauli operators. Basis will be eigenstates 0 and 1. Okay, so these are the basis states 0 and 1, or you may just think about them as a vector space with these 2 orthonormal bases that I'm writing here. Now, what are the Bell states? Bell states are given by this, which are actually the 0, 0 when I write it is a tensor product of 0 with another 0. So 0 in A and 0 in B. Here we are not, it's a shorthand form of writing 0 tensor 0. Just put both of them together. So this is an entangled state, and it's in fact these states are called Bell states after John, in honor of John Bell, and you can see that actually they are orthonormal states, and they will form themselves a basis in this. So let's take any one of them. I've taken here plus minus, but let's take plus. It doesn't matter. So this will be the state of the photons with A and B. They are entangled. Okay, and this is the state of the unknown photon with Alice, which she needs to teleport. She doesn't know what alpha and beta are. She just knows that you have some state like this. So this is the joint state of the 3 photons in the picture. Alice has A and C, and Bob has B. Now, you can rewrite the state, and it's just elementary linear algebra rewriting like this, where these are the Bell states of now the photon pairs with Alice. So now you can write this as a linear combination of maximally entangled Bell states along with some other states of Bob. Okay, now the important thing is that these are orthonormal states of the two photons with Alice. One of them is actually the unknown state. But you see, interestingly, you can already see what's happening. There is some magic which has happened. With this alpha and beta was with this C index. Now they have gone to B. Nothing has been done. It's only a rewriting of the state. It's just coming from the linearity of quantum mechanics that this alpha and beta gets transferred into this state for B. But nothing has been done here physically. Now what Alice does is she makes what is called a Bell measurement or a joint measurement of A and C, in which case she will get one of these states as an outcome, phi plus or phi minus or psi plus or psi minus with probability 1/4. Let's say that she gets the state phi plus, just for argument. That's 25% of the time. What do we see as the state of Bob? Alpha 0 plus beta 1. But that is precisely the state that of the unknown spin that was there with A. So even without doing anything, 25% of the time, just by doing measurement, Alice's joint measurement, Bob's qubit will somehow magically acquire the state of this unknown qubit with Alice. So indeed, she can make it 100% by sending these two qubits so that he can be sure which one of these four states he has got. Okay, so that's actually the mathematics of teleportation. The most hard part of this from an experimental point of view is to not make this entangled state, but is to make this joint measurement. Okay, that's my understanding. Are there any quick questions on this mathematics? Because that will be the end of this mathematical tools section. Sorry if there is some extra noise. I'm in a construction zone. So let me then formally define what is entanglement. Okay, and n particle Hilbert space. Now I'm going to not only two particles, but n particle Hilbert space. A state is unentangled if it can be written as a pure state is unentangled if it can be written as a tensor product of these things. Otherwise, it is entangled. I'll come to mixed states maybe a little bit later, or maybe I won't have time for mixed states. I will see. So let's look at very simple examples. Let's take this, what is called a spin singlet state. Right? And if you're thinking about it as spins, up, down, minus, down, up, is a spin singlet, which is a common state of two electrons, let's say in a hydrogen molecule or something. So you have this state. I claim that it's an entangled state. To justify this claim, we have to try to write it as an unentangled pair of this alpha and beta, and you can assure yourself you should actually convince yourself that it is not possible for you to write it as a product of two. I'm sorry to use this. Alpha and beta should not be confused with the coefficients which I have used earlier. These are just two states for psi 1 and psi 2 or psi A and psi B. It's not possible to write this. And therefore, in a spin singlet state, it is not possible for us to assign the spin state of either one of these particles. Let's take a look at this state, which is a superposition of 0, 0, 0, 1, 1, 0, and 1, 1. This looks like an even more complicated state than the singlet, and it looks like maybe it's an entangled state, but actually it's not, because it's just a tensor product of these two states, which are like each of them is a 45-degree rotated state. So 1 plus 0 and 0 plus 1, or 0 plus 1 into 0 plus 1. You see, tensor product, that's what I mean by into, will give you this. And therefore, this is actually an unentangled state. So in general, a 2-qubit state, a general 2-qubit state is a combination, linear combination of these 4 basis states, 0, 0, 0, 1, 1, 0, 0, 1. This is just a special case of what I have written down here, with dA and dB equals to 2. And I'm representing the bases as 0 and 1. That's all. But how do we decide if this state is entangled or not? Clearly, the answer depends on these coefficients A00, A01, A10, and A11. For what coefficients will it be possible to write it as a product, tensor product? For what coefficients is it not possible? That is a basic question, whose answer I will now say what it is. So one of the things which you can work out, and I encourage you to work out yourself, is to just see whether it is possible to write this or not, and you will realize that it is entangled, that is, you cannot write it like this, unless the determinant of a matrix A, which you get by writing down this A00, these coefficients in a matrix form, 2 by 2 matrix form, if the determinant is 0, then it's unentangled. Otherwise, it is entangled. Okay, so what we are doing, the basic trick is to identify these coefficients of this state as a matrix and to look at the properties of that matrix. Okay, so that is what we will generalize to higher dimensions also, arbitrary dimensions. So we will call this, let's say, matrix of coefficients. It's in general a complex matrix without any structure. What is the importance of this matrix? So this will involve some more mathematics. And now I'm going to answer the question as to what is the state of individual subsystems. Although they are not states as we know them, they are actually what are called reduced density matrices. So they are in some sense generalizations of states. So let's take now, instead of A and B, I'm going to call it 1 and 2. This is a 2-particle state. Okay. Now the state of these 2 particles can also be written in this form, psi1 2 outer product psi1 2. So this is called a density matrix for those of you who know this, because the phase is not important. Overall phase is not important. This will remove an arbitrary overall phase, and there's just a projector of this. So this is the state or a density matrix of this particle psi1 2. And you see, this is a pure state density matrix, is a projector of rank 1. It's a projector of rank 1. It's just an outer product of a vector with itself or with its conjugate. So now, if you do a partial trace, you trace out subsystem 2, you will be left with only a state of subsystem 1, and that is called a reduced density matrix. Okay, so tracing out the trace operation you are familiar with, but you don't do a trace of the full system, you do only a partial trace. You do a trace over subsystem 2, then it gives you state of subsystem 1. And exactly how you do it, you can put this state in here, and you can do this manipulation. When you're doing trace over 2, this Greek indices will disappear, and you will be left with only this one here. So I'll give you the result of this. The result is that the density matrix of subsystem 1 is given by a product of A tensor times A adjoint. This is just an ordinary product, no tensor product. A into A adjoint, where A adjoint, you know, is transpose conjugate. Okay, it's the transpose complex conjugate, or it's the Hermitian adjoint. A adjoint, where this A is this matrix, which I wrote down here. It's a generalization of this matrix. So I've just written it down here. AI alpha is this matrix. So it's a dA into dB matrix, in general rectangular, but rho 1 will be an n by n matrix. Okay, where n is, here I am sorry again, this n is what I call dimensionality of subsystem A, m is the dimensionality of subsystem B. I used dA and dB before, I'm using n and m on this slide. Okay, so this is the reduced density matrix. And you can detect the entanglement or not if and only if rho 1 is a pure state, then it will be unentangled. Okay, So how do we find out if that is the case? We just have to um, uh, find out the eigenvalues of this reduced density matrix, and that will tell you. So in fact, this comes to a very central part of entanglement theory. It says you diagonalize the reduced density matrix. You see, this AA adjoint is a Hermitian matrix. It's in fact positive and Hermitian, and therefore you can diagonalize it. You can find eigenvalues which will be all positive numbers, lambda I, eigenvectors that are orthonormal, and similarly, the reduced density matrix of subsystem 2, you can find out eigenvalues and eigenvectors. And the very important and remarkable thing is that because it's a pure state of two particles, both the reduced density matrix of 1 and 2 will have the same eigenvalues, lambda I. The set is the same. And this is called the Schmidt decomposition. It says that this is how you can rewrite the state of two particles in the most economical way, in this way here. Rather than writing it as a sum over n into m terms, you can write it over only n terms. And these are the eigenvalues of the reduced density matrix. And finally, the answer as to whether something is entangled or not, if one of these eigenvalues is 1 and everything else is 0, they should anyway sum to 1 from normalization. So if any one of them is 1, then the state is unentangled. Okay, so this may seem like a slightly long, technical thing, and indeed it is. I'm not. I would have preferred to use a board. It's a 1-hour lecture for this, so don't worry if you don't understand it and if you're looking at it for the first time. But let me just emphasize that it's a very central aspect of entanglement, and anybody who wants to understand it must understand this basic linear algebra. And the answer to the question about whether such a state is entangled or not depends simply on the matrix whose entries are these complex numbers Ci alpha, and that answer is coming from the diagonalization or the eigenvalues of this matrix C times C adjoint. If its eigenvalues are just 1 and all other eigenvalues are 0, then the state is unentangled. Otherwise, it is entangled. And in fact, this leads us to a measure of entanglement. How entangled is a state? It can be 0 entangled or not. So this is coming from the von Neumann entropy of these reduced density matrices. So this is the entropy of the reduced density matrices, and because the state of the whole is a pure state, the entropy of subsystem A is equal to the entropy of subsystem B, and that is equal to these eigenvalues in terms of the eigenvalues of the reduced density matrix is given by this, and therefore it is 0 if the state is unentangled, and this von Neumann entropy of a reduced density matrix is maximum if the state is maximally entangled. So let me say that there is a connection between entropy and entanglement, and in fact thermodynamics and entanglement. So it's a very interesting connection which you can see coming from entanglement theory into entropy. So it's a very tantalizing thing. I've just given you a very small and very brief and probably ununderstandable analysis of this, but the structure is actually very simple and based on basic linear algebra. So let me skip this and let me ask if there is any question about this technical aspect. Pankaj, has entanglement or Schmidt decomposition been introduced in other talks? Hello?
Yes, sir. Continue, or because of some internet problem.
Okay. Yeah, fine. So I am audible, right? Okay.
You
So
are audible, sir.
I'm going to continue. So I'm going to now give some further properties about entanglement. One of the important properties is called monogamy. So now let's take a state of two particles, one blue and one red, and both of them are, let's say, in state 0. Okay, so this is now the state of unentangled state. Let's say that we entangle them. This is in general an entangled state. You can in fact find out what is the amount of entanglement by doing exactly what I have now said. In fact, we can use this. We can say that it is already in a Schmidt decomposed form, and the entropy or the entanglement is just given by a binary entropy, where the probability is modulus alpha square. Okay, so that means that if alpha is 1 over root 2, it will be maximally entangled. So this thing is a maximally entangled state. As you can see, it's also a Bell state. Now, if there is a third particle, a green particle, let's say that it's in state 0, can these two particles be entangled with this green particle? The answer is no. So if two particles are maximally entangled, they cannot share their entanglement with other particles. This is called monogamy. And this is not a property of classical correlations. Classically, any number of random variables or particles can be maximally correlated. Okay, so you see here, if these two are maximally entangled, red and green, then it will lose entanglement with the blue particle. Of course, there are states in which all three are entangled together, but in this case, no two of them can be maximally entangled. For example, here I've written a state like this. This is the entangled state of these three particles. Okay, this is another famous example of a 3-qubit system called a W state, where it has the symmetric form 001, 010, 100. And this is the GHZ state which I wrote earlier, which is of this form 000 plus 111. Now I have put some kind of a line all over this thing to indicate that such a state is maximally entangled. Not only maximally entangled, it's also what is called maximum tripartite entanglement. Okay, this is different from the state which I showed here. In this case, there is entanglement between these two particles. There's entanglement between these two particles, entanglement between these two particles. So there's pairwise entanglement, but there is no entanglement between all three taken together. This is the issue of multipartite entanglement. Whereas this one has that. It has no entanglement between any two of them, but there is entanglement between all three of them. This is very funny because it seems very strange. Let me skip over this due to lack of time. So, as I said, the GHZ, all three are entangled, but no two are entangled. How do we show that? We find out the reduced density matrix of, let's say, 1 and 2. Okay, we trace out particle 3, and then we get this density matrix here. I claim that this density matrix corresponds to an unentangled state. And that's because I did not define what entanglement of a density matrix is, so you won't know it if you have not seen it before. So let me tell you that a density matrix of 2 qubits is separable or unentangled if it can be written as a convex sum, that is, all these pi's are positive numbers that sum to 1, of products like this, rho IA, rho IB. So these are separable states themselves. If they are linear, if they are convex sums of separable states, then such a state is itself unentangled or separable. And this one is exactly like this, because P1 is half, P2 is half, rho IA is just 0, 0, rho IB is 0, 0, rho 1, rho 2 is 1, 1, and rho 2. So this is actually an unentangled or separable state. But clearly this cannot be written as a product of 3 pure states, and therefore it's entangled. So let me give you some metaphors for such possibilities. Here, completely classical, something that you should be able to imagine. I have taken this. This is a book on entanglement theory by Bengtson and Shishkowski. Uh, Here are three rings in what is called a Borromean configuration. Three rings. You see, they all look very interlinked. But if you imagine only two of them, and if you remove the other one, just imagine that there are two of them. Let's say this and this ring and this ring. You see that this ring is totally on top of this. Therefore, it's not linked to this. Similarly, this ring is totally above this ring. You see, and therefore it's not linked to this. So pairwise, none of these three rings are linked to each other, but overall they are linked to each other. So you cannot remove them; they are interlinked. So this is actually possible to do, and you can go ahead and do it. You should do it. It's possible. So entanglement is like this. So tripartite entanglement is like this in the GHZ state. It's possible that no two of them are entangled, but all three together are entangled. By the way, you can look at Gwalior seems to have a lot of historical structures. This is from a temple near my house. You will see exactly this. And I don't know, temple maybe 10th century or something. In rectangular forms, you can see three rectangles with the exact same property. That is called a property is called Borromean. Okay, so these are metaphors for multi-partite entanglement. So let me not let me actually end because I think I don't have much time. We might ask some questions and so on. So entanglement is a resource for many things, including teleportation, as I mentioned. So Bell states are maximally entangled. GHZ states are in some sense maximally entangled. You can look at it as entropies from von Neumann entropy. Maximally entangled states are very useful for teleportation. They're also very useful for error correction codes, which is, as you know, crucial for any quantum computing. Secret sharing, like in cryptography. Dense coding, I have not mentioned, but maybe others have. And if you go to more than three particles, it becomes even more interesting. You can ask if there are maximally entangled states of 4 qubits. Actually, they don't exist. Such states are not maximally entangled states of 4 qubits. So absolutely maximally entangled states. So there's a lot of work going on currently about these states, characterizing entanglement in many particle or many qubit states. Is quite easy to do, and but very interesting things. And there's a lot of applications in matter and space-time. A lot of applications in condensed matter physics, as well as spin chains are very natural things to study as models of quantum computers. You have a qubit, as I mentioned, two-state system or spin half particles, but arrays of them that are interacting. They have been studied in condensed matter for a long time, and such spin chains are actually quantum devices, and therefore qubits as spin chains are a very important system to study. There are recent developments in quantum condensed matter physics, such as quantum phase transitions, many body localization, which is a very important area, which is like Anderson localization but with interactions. And a quantum computer must presumably be in actually a many body localized state for it to be not going into chaos. And in fact, quantum chaos and thermalization studies, there's a lot of things about entanglement, atomic and nuclear systems, space-time itself as entanglement. So there is this whole areas in string theory, ADS, CFT correspondence and entanglement, tensor networks as models of quantum gravity. I'm just giving you some, key words of today. Black holes, you may not think that black holes have anything to do with entanglement, but actually there is a lot to do with entanglement and information scramblers. Basically, entanglement leads to information spreading in a many particle system. So that's called scrambling of information. So black holes are supposed to be the fastest scramblers and very chaotic in some sense. So space-time itself as a quantum many-body phase in which entanglement is an important aspect of space-time. So after about 85 years, entanglement is now being measured and understood as a fundamental property of space-time and matter. Much more to be explored. There's a lot of areas, quantum error correcting codes, tensor networks, where basically you have a network of qubits, or you have qubits that are in some networks and they are interacting and so on. It's a very interesting set of states called absolutely maximally entangled states. I didn't talk about measurement itself, except in a Bell measurement situation, but that kind of also tells us, how does classical world arise? We don't see any entanglement around us. How does classicality arise? And many body systems, multipartite entanglement, relativistic and field theoretic systems are now being investigated. So there's a lot of interesting work that's going on. There is a lot of online resources, of course. There is the archive. If you look in the quantum archive, you get almost all people put it there. So for free, you don't need uh, any subscriptions to any journals. And there is John Priscill's notes from Caltech, which are freely available. So all you need to do is get entangled yourself, and I hope that my talk will at least tell you that it's not it's interesting and also easy to do. So thank you all for your attention. Let me stop here because it's 5 to 1. Hello.
Sir, there is actually a network problem we are facing. Okay, so continue, sir. If you are adding.
I'm actually done, Pankaj.
Okay. So it's time for questions from our
Yeah, I
participants.
thought I should have some time for questions because it's only 5 minutes more.
Yeah. Any questions from our faculty members, research scholars? Yes. Any doubt? Any questions? Okay, sir. I think.
So I will share the slides with you. I mean, if people are
Stop sharing,
interested.
sir. Please, you can stop sharing, please.
Yeah. Yeah.
Okay, sir. Okay. So thank you very much, sir. I think that's a very wonderful lecture on the quantum entanglement, and from basic to applied. There is journey from in your lecture, starting from basic to go for applied kind of things. And I think the faculty members have enjoyed a lot in
Thank you very much, Pankaj,
this
and thanks for
session.
the invitation. And I hope that it will be useful. Yeah. Thanks.
So thank you very much to everybody.
Thanks. Bye. 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 Bye, everyone. Bye, Pankaj.
Yeah, it's audible to you, sir. There is some internet problem right
Yeah.
now.
Yeah. I can see that. I think it's low or.
Yeah, actually from night there is some problem when WhatsApp, Facebook, everything goes down.
I see. I see. I see. That's
So
a pity. That's a pity. Yeah. Yeah. And yeah. But anybody, I mean, I will send the slides, and I'm sure that there are many interesting talks which will. Thanks, Pankaj. Thanks, everyone. I will close this now. Bye.
is I audible to everybody?
Yes, sir.
Okay, so we can meet at 2 p.m. right now with session 6, that is teleportation and super dense coding by S. Adhikari from Delhi Technical University. You must join there. Okay. Okay. Have a nice day.